Again, this is Lab 8. Today is October 15th. And today's lab is pertaining to waves, basically. This is different than the previous labs. It's almost every lab that we do in this class is different than the previous ones. This one is basically, there is the instructions, and also going and doing a bunch of videos you're going to be watching. So you really have to pay attention to step by step, okay? There is not much anything I can honestly say about this lab other than you guys have to read the instructions, watch the video, and answer the questions. So this is in a nutshell what it is. So that's the only thing I can tell you for this lab. So if we fail to skip one step, we're not going to be able to answer the question. The only thing I can tell you also up front is question 7 is optional, okay? So that is the thing that you're going to put in your discussion toward the end. We were instructed to do or not to do question 7, okay? Other than that, everything else is not optional. Everything else is mandatory in order to earn a grade, of course, okay? So that's the only thing I'm going to tell you up front for this lab. Had anybody looked at this lab before, right now, before 6 p.m. today? I know I posted it late, posted it last night, I think, very late. But did anybody have the chance to go through it?
Did you say that we weren't gonna be able to stay in the group later on?
Okay, hold on. For some reason I can't hear you. Is it my screen or the voice is kind of very far? Can you speak up it again, Jose?
I was wondering, I came in late, so were you saying that we weren't gonna be able to stay the entire time?
Well, probably the thing with it, what I was saying is this lab is different than the others.
Okay.
You have to actually go through every single step and read the instructions, read the definition, okay?
Uh-huh.
Watch 1, 2, sometimes 3 videos first.
Uh-huh.
I have to go through them, notice things related to amplitude, related to waves and everything. There is the first part which we're going to do together because it should be easy enough to go through the activity. But the rest, you really have to do it at your own pace, okay? And then answer it based on that. So there is a bunch of 24 questions altogether. Out of the 24 questions, question 7 is the one that I'm telling you is optional. Actually, I was thinking to remove it completely, okay? So right now, whether you answer it or not, it doesn't matter. So I'm hoping that some of you will spend time after you finish everything to see it. But again, it's not going to be counted. So that's the only thing that is different. Everything else is the same, okay? Everything else, you're going to go through it.
Okay. And so basically, it's just gonna take longer, but I mean, we're still gonna be in the group.
Yes, I'm gonna be here, okay? But it's not gonna be enough. That's what I'm saying. And here, honestly, you really have to spend all the time through it. So it's not gonna help much if I tell you here is the question like what we used to do. But there are parts that we're gonna do together, okay?
Okay.
So let's go through this. So again, the instructions are the same. The only thing that is different this time around is, other than question 7, which is part of the discussion, is now you have 2 PDF files you need to download, okay? In the instructions, it tells you download this one and download the other one. The second one, it does not tell you specifically to save it on your computer and all of the stuff that you have to open it with Adobe Reader, because honestly, all you need it is just for your the data from it. You're not gonna write to it. So the second PDF file is not writable, it's not fillable. So that's the only thing that is different. Everything else is standard in terms of how we get this one. Please do not forget that you have a rubric. This rubric is kind of straightforward because you don't have tables, you don't have graphs, you don't have a lot of things that we used to do in the other labs. So this one is straightforward in terms of gradings. There is a point for the name and the names. There are 3 points for the objective. Remember, the objective has to be at least 2 sentences or more. Complete sentences, not basically short words. The questions, there are 24 of them, -1, so it's 23 really. Each one of them is worth 2 points. You get the full benefit if you have the answer in complete sentence. Also, if it has numbers, the numbers will have units attached to them, and it's graded for accuracy and units, and also the structure. Okay, you miss any of that, you get less points, and so on and so forth. So that's the questions. And at the end, you have the conclusion, which is worth 5 points. Don't forget to tie in your conclusion to the objective, and the conclusion requires a minimum of 3 sentences. In this case, because we really don't have a lot of data, you may get away a little bit without data, but you need to break it into connect it back to your objective. Okay. And technically, any conclusion must have some data to support it. You cannot say that it agrees with or doesn't agree with. To some extent, with how much confidence it does or it does not depends on data. So that's basically how this lab is structured, like anything else, like all of the other labs we've been doing. Okay. So let's share screen and look at the instructions. Okay. So again, it's all about waves. Don't forget your name. When you see a red thing in here, that is a required field. This is also required, the objective. Please don't start with the objective right away. I know in here it talks about how much daily things and waves and things like that. That is not your objective, okay? Your objective is after you read this thing, it's divided into different sections, as you can clearly see. Wave properties, what are the properties of a wave, okay? I'm going to skip these things, but I'm expecting that you guys don't skip it. You're going to read through this. I'm going to come in here. This is a wave drawn in, because a wave basically is an oscillation that propagates in space, okay? You know how pendulum, for example, goes back and forth? That is an oscillation, okay? If you have, what is my, oh man, here. If you have a spring, for example, and you attach a mass to it, it oscillates too, okay? This is actually a slinky. It doubles as actually a medium where waves can propagate. If I compress a region of the spring and let go of it, that disturbance, which is the compression that you guys see in the near my eye and here near my glasses, if I let go of it, it's going to propagate throughout the medium. So again, it's compression. This is a compressional wave, okay? Unlike a transverse wave, which is in this case, I'm oscillating it, so I have a source in the bottom, and this is propagating throughout the medium. Because I also have the other end that is fixed, so actually I have standing waves now on this, okay? They're not uniform standing, they are not in resonance, but there is standing waves on it, okay? Because the wave bounces off of the other end and comes back. So wave is actually a disturbance that travels in space. So it has a temporal behavior in time, and it has a spatial behavior in space. So that's basically what a wave is. So again, here is a wave. It's the disturbance is changing with time. Let's say, for example, take somebody freezes time. You take a picture with a camera of a wave. It looks, at least a harmonic wave, looks like a cosine or a sine function. That's what a harmonic wave. Not all waves are harmonic, by the way. They don't have to have this behavior, this nice feature of going up and down and things like that. Sometimes they be complicated waves, so they don't have to have that. This is called the harmonic when it's a sine. This is definitely not a harmonic. This is a complicated form of a wave, which is most of the time, okay? So that is what a wave is. So wave is a disturbance that travels in space, okay? So it is characterized by, or it has several properties. First of all, in terms of the temporal behavior, the time it takes for a wave to go back and forth to its initial state. So we left it from here, okay? So it's gonna leave, go to the other end and come back to the same state. That time is a period. The period is measured in seconds. It's a time, okay? So it repeats every single period. The wave repeats every single period. This is a temporal behavior. Also, the shape of the wave, if you take a picture of it, it repeats every distance, basically, over a distance, which is called the wavelength. After every wavelength, the shape of the wave repeats. I'm looking at the point C in here in this graph, for example, and the point I, they look identical, okay? They are both peaks, okay? The point F, on the other hand, this is a maximum for the point I. The point C is also a maximum. The point F also is a maximum, but in the opposite direction, okay? That's a trough, okay? So these are not, F and I are not identical. The point G, for example, the point E and the point A, the wave does not have any displacement along the positive direction or the negative direction, okay? So in this case, those points are actually have their displacement 0, okay? So those are the so-called nodes. They don't move, they're stationary, but they're not identical. The point A, for example, the wave was coming from the negative side toward the positive side. The point E, the wave was coming from the positive side to the negative side. So this points, the distance between A and E is not a wavelength. However, the point A and G are identical because the wave in this case was coming from the negative to the positive and it passed through the x-axis. The wave also in the point G was coming from the negative to the positive, and it is 0. It vanishes at that point. Since this is the first occurrence, the first time this happens after the point A, this distance from A to G is also wavelength. So the wavelength is the distance from similar points. When I say similar, that means the wave is identical in behavior. The point B, for example, has the same magnitude as the point D, has the same magnitude of point H, and there is another point in here I didn't draw, but the point J, for example, they're all identical, okay? They have the same magnitude 1 for the displacement. They're not maximum, they're not 0, they're somewhere in between, okay? But in the point B, the wave is going toward its maximum. The point D, it is not going toward its maximum, although they have the same value, but they are not identical. So actually it's coming from its maximum in here. So this point B and D, the distance is not a wavelength. However, the distance between B and H must be a wavelength. That is the distance, because in H also, it has the same magnitude as B, as much as D also, and it's going in the same direction. It's going towards its maximum. So H and B, the distance is actually a wavelength. As a matter of fact, the distance between D and this point I didn't draw, J, is also a wavelength. So the distance between D and J, B and H, C and I, A and G are the same distance. That is what we call a wavelength. The symbol for wavelength in all the books is lambda, the Greek letter lambda, okay? And as you can tell, it's a distance. It's measured in meters, okay? So that is two characteristics already. The point C doesn't stay in its place. It goes up and down. Sometimes it's up, like right now, it's a maximum, but it's going to move down. So if you happen to be, if this is the surface of the water, for example, and you're sitting on top of, and you have a boat that is in this point in here, so the boat at some point will come down, and it's going to be the level of the sea, and then it's going to go below the level, and then it's going to climb back up to the level of the sea, and then it's going to rise again. So the boat will bob, basically go up and down, up and down, up and down. The time for the point C to go the entire cycle from C down to 0, down to the negative side, back to 0, back to where it was when we started this, is a period. That time is actually a second. That is the period. That is also a characteristic of the wave. Same thing. if I wait for the point C long enough, and let's say the wave is traveling to the right, the point C actually is going to be replacing the point A, so it's going to come down. I mean, the point B is going to replace the point A, so it's going to come down, then go all the way to the negative side, and come back to 0, and go back to its current position, but that's not in the same state, because right now it's going down, and when it comes back, it's going up. So that is not the whole full period. I have to wait for it to climb back to a maximum and come back to B. So the fact that I did not start at a maximum or a minimum, if I started somewhere and it's coming down, so this is my starting time. So this is when I click on the timer. So now it's going down. It went all the way down, came back up. By the time it reaches this point, back up. That is not a period. I have to wait for it, because if I wait for it, it's going up. It's not coming down. So it's going to go back down now to the point B, where I can say that is a period. So that is the time for it to come back to its original state. And that time, after I click the second timer, that is what is called the period. So we have two characteristics at this point. And the two characteristics of the wave so far, let me get my, because some of you probably like to write it in here, so let me get my pen. So the two characteristics so far are lambda, and this is what I called a wavelength, and a wavelength is a length, and it's measured in meters, okay? The second one is a period, and usually we write a T, and this is what we call a period. And this is measured in seconds, okay? So those are two characteristics. This one is a spatial behavior, whereas this one is a temporal behavior, time. For this one, you need a camera. You need to freeze the wave with a camera, okay? Freeze time, if you like, okay? For this one, you need to be on a specific point, like a boat sitting on the. You're sitting on a boat and on the on the ocean, okay? So this is on a specific point in space. And then you have the clock changing, okay? So you don't freeze time for this one. So these are some of the characteristics, basically, of the, oops, I don't mean to change this, leave it there, okay? Of waves. So those are some of the definitions. There is another concept, is how fast the wave moves. The wave moves with a speed which is lambda over t. Remember, lambda is in meters. The time is in seconds, so this is the speed of the wave, okay? Meter per second. Another useful term, another useful property of the waves is the so-called frequency, okay? The frequency, by definition, if you wish, is 1 over t. How many times, let's say, for example, I am on the boat, okay? And all I care about is 1 second. If the boat goes down and back to its initial state in 1 second, then I know the period is 1 second. I say in this case, it does 1 cycle per second. But if it goes up and down twice in 1 second, that is faster. You guys see that? So it goes twice per second. So the period in this case is a half a second, because it takes half a second for it to go up and back and it's forth. By the second half, it would have done 2. So another way of characterizing how fast the wave go up and down is the frequency. And the frequency is the number of times, so this is the frequency, is how often, if you wish, a wave will change in time per second, okay? So the unit for it is 1 over second, but again, 1 over second has a different name now. It's just for convenience. It's called Hertz, okay, in honor of Mr. Hertz, who did a lot of work in here. So those are the 3 characteristics of wave so far in here. Actually 4 right now with the velocity. So the velocity in terms of the of also the frequency, because 1/t is a frequency, can be also written as lambda f. So this is the math. This is the algebra we will need for this lab. Okay. The wavelength and the period are measured with first one in meters, the second one in second. Since these are the only distance in town and the only time in town, then the ratio of which is meter per second, that is the velocity of the wave. Another convenient way to represent how fast the wave is moving up and down, basically changing with time, instead of using the period, which is how long does it take for it to go back to its initial state. If it happens a fraction of a second, instead of doing that, I can count how long it's going to go back and forth in 1 second. For example, your cell phone is using a gigahertz, 5.5 gigahertz or 2.4 gigahertz. That is billion times per second. It goes back and forth. Except in that case, it's a different kind of wave, which we're going to discuss their types today. So these are some of the properties of the waves. Okay. One final property that we will need for the definition today, and that is wave packets. So this is a single harmonic in here. All of this discussion is for one wave by itself, okay? What if I have, let me get another one in here. What if I have more than a wave, okay? So I have 1, 2, 3, and 4, and 5 of them moving together. Each one of them can have its own velocity. As a group, the entire packet will have something called the group velocity, okay? They may disperse, and we will see that, or they may stay together in a packet. So that's another property. It involves a different concept, but this is the general behavior of waves when they come in droves, not just a single wave, okay? So that's typical how things are. In the ocean, for example, you don't have a single wave that is moving, okay? So you have different waves coming together, and the entire bulk of waves moving from one side to the other is a group. In this case, it's moving with a group velocity. Now, if the leading edge of the wave starts to move faster than the slower edge, then in this case, they start to disperse. Okay, that is dispersion of the waves. If not, if they're moving with the same speed, then they stay together. The group velocity, more or less, will be the same velocity of each and every one of them. Okay, so that is another concept we will need, and we will talk more about them as we go along in the instructions. So I'm going to stop this screen and go back to the instructions. I'm counting on you guys to read the instructions more, okay? And let's get into the question. Which pairs of letters on the illustration could be used to calculate the wavelength, and what is the wavelength of the wave? Okay, I already gave you the answer to this question. Can anybody help me in here? We need a pair of numbers to calculate the wavelength.
Would it be A and G?
A and G is good. Another one?
CNI?
CNI, that's good.
Sorry, man.
No worries. B and H?
B and H are good, yes. That's the only ones actually in this graph that are listed. I didn't mention J in here, but J actually, the point after I actually can be used also with D, okay? Correct?
Yep.
Okay, so that's the answer to first part of the question. The second part is what is actually the wavelength? So which ones are easier to measure the distance between them?
I would say between B and C. Or wait, no. Yeah, right. Wouldn't you do that? B and C.
B and H?
Oh yeah.
B and H. Does everybody agree that B and H is the easiest one?
I would say that because like it's a smaller distance that you can calculate.
I think it's the same distance, like from A to G, B and H, C to I.
Yeah, it's the same distance.
Just kind of shifted, yeah.
But which one is actually easily labeled on this graph that you can do the difference much quicker than anything else?
B and H is easier because it's literally just one apart.
Okay.
1 meter
Oh, I
apart.
see that. Yeah.
Okay. So what is the wavelength now?
1 meter.
Yeah, 1 meter. The unit is in meters. So 1.25 meters minus 0.25 meters, that should be 1 meter. Good?
Yep.
So that's the same
Yeah.
distance between C and I also, the same distance between A and G, the same distance between D and J in here. I didn't write J in here, but that's the same thing. Okay? So that's easy enough. Question 2. Which pair of the letters above could be used to calculate the amplitude? That's another thing I didn't talk about. The amplitude is this distance from the origin to the maximum point or to the minimum point. That is your amplitude. Okay? It's how strong the wave is. In this case, the amplitude, what are the points that I can use to find the amplitude?
Would it just be like the two maximums then? You said?
C or F, right?
How about the other one? There is another one.
I.
Yes, C or F or I. One of these three can be used. Okay? Okay, and because it's a distance, we don't care about the sign, okay? It's just a distance. So it's going to be an absolute value. We don't care if it's negative or positive. We just want the actual value, the numerical value. Now the second part is, what is the amplitude for this wave? Use either any of those points.
Would it be like 1.4?
Does
It's
everybody
okay.
agree?
Yes.
It's in relative units. It's not stated. The reason why is relative units is because it could be, for example, on a string, it's in centimeters, okay? It's up and down in centimeters. On a sound, for example, it's probably decibels, okay? The intensity of sound, okay? On light, for example, it could be the amplitude of light, which is measured in the square of the electric field. That's why the units for the amplitude depends on the situation, what you're doing. On the water surface, for example, it's in centimeters. That's how high, what's the maximum? I'm talking about a pond. I'm not talking about the ocean, okay? On the pond, it's in few centimeters, okay, compared to the pond in there, which is in usually much more than, it's in probably tens of meters, okay? On the ocean, it's probably going to be in few meters, okay? So if the ocean is very, very violent, it could be 4 or 5 meters. That's too much, okay? That's a lot of wave. So that's basically the distance. That's why the unit not in here stated. So the correct answer is 1.4, whatever units you're talking about, because this is a generic wave. This is not a specific kind. Yes?
For the first one, we put that it would be 1 meter long, right? The wavelength.
Yeah, you have to tell me how you got it in this case, because we said that it's easier to do B and H. So you can say the distance between B and H is 1 meter, 1.25 minus 0.25, okay? But also you could have argued that it's A and G, okay? Or C and
Right.
I, okay? So if you have a ruler and you have to convert the unit correctly, you could also see that, okay?
Okay.
But don't forget there is a first part to the question which lists the points. You have to list the points. So, and there is second. Both of them have 2 parts. Both 2 questions have 2 parts. Okay. Now there are 2 kinds of, the wave actually doesn't stay in its place. It moves. So this is a so-called right moving wave, because the wave can be moving to the right and the wave can be moving to the left. Where is my slinky? Here. Okay. Let me illustrate that with the slinky. Okay, in this case, the wave can be created from the bottom and can travel to the up, or the disturbance can be created from the top and can travel to the bottom. In general, it can go in both directions, okay? It can travel in both directions. So in this case, the point A, 1, okay, has shifted to the right, And that is the velocity I was talking about. It moves with a velocity v, and that is the velocity of the wave, okay? The velocity of the wave in this case, on how fast it moves one way or the other. That depends on the medium, which brings me to another kinds of waves later on. We'll talk about waves. There are some mediums that don't exist, and yet they have waves in them. So there are some weird waves that we need to explore during this thing. So waves are really a common phenomenon, and they do travel, and they travel with a certain velocity. So here is the situation. I create a disturbance in here, and take any point later on. It doesn't matter where the point is. It waits until the front of the wave hits it, and then it displaces up and down, or left and right, okay? Depending on the type of the wave. So if you guys paid close attention, somewhere in here, or anywhere else where it created a disturbance at the bottom, the wave will hit it, okay? And will make it move back and forth, okay? None of these rings actually moved all the way to my other hand. It's only the disturbance that moved, okay? So the material itself did not move. What moved was actually the disturbance, same thing. What keeps on hitting you if you are in the ocean is actually the same water that you're sitting on it. It's not the water came from the other side of the ocean. So it's just that water that goes up and down and probably goes in a circular fashion. We'll talk about it when we talk about water waves. Okay? So again, this is what I was talking about, the frequency and how it's related to the period. And the velocity is lambda, which is the wavelength over the period, and lambda f, okay? For example, if lambda is 1.2 meters, and the period is 0.4 seconds, you can easily find the frequency, which is 1 over 0.4 seconds, okay, which is 2.5 hertz. And the velocity in this case is 1.2 divided by 0.4, or 1.2 times 2.5. It's the same thing. It's going to end up being 3 meters per second. Now, there is a calculator. You can click on it. This is a GeoGebra, okay? You can click on it, and you can enter whatever values you can that was given to you, and you should basically do the calculation for you. That is, if you don't have time to do these calculations yourself, okay? So here's question 3, I'm sorry. Suppose that a wave has a wavelength lambda of 3.6 meters and a period of t equal to 1.6 seconds. Calculate the frequency and the wave speed. So we're gonna need two things in here. We need the frequency, which is in hertz, and we need the wave speed. If you want to, you can do the calculation using your calculator. Alternatively, you can click on this link and it should take you to the GeoGebra. So let me click on it so that you guys see how that looks like. So I'm going to click on it. And once it pops up, I'm going to stop sharing that screen. I'm going to go and share with you how it looks like. This has a lot of other things, okay? So you're going to put in the lambda that was given to you, you put in the t that was given to you, and this will give you the correct stuff. Don't click on the animate because that's a different activity for another thing, okay? So this is easy enough, not? I hope that you guys will have the F, which is going to be in hertz, and the velocity, which is going to be in meter per second. And don't forget that this is question 3. Alternatively, as I said before, you can use just a calculator for that. Does this question make sense to you guys? Yes, no?
Do we have to
Full sentence, yes.
do we have to basically we do the lambda over t, right?
Yes, that's for the velocity.
Okay, for the velocity. And then to find the hertz.
Yeah, frequency. You do 1 over t, that's it.
1 over t. Okay.
Or you use the GeoGebra link, okay? One of the two. Now, I need these things in full sentence format and also with the units and the numbers and everything else, correct?
Yeah.
Okay. Now, this is a general question. How are the wavelength and period or frequency related to the wave speed? So this is basically, you need to explain what this relationship means. Okay. This has a different name. Sometimes it's called the dispersion law. Okay. So this is the dispersion law. And is the amplitude related in any way to the wavelength, period, or frequency? Look at this expression. The amplitude, the symbol for the amplitude is capital A. Do you see it anywhere in here? Or in here? Okay. Is it related to it or not, according to what we see? There are two parts to this question also. I want somebody to confirm, is it related or not? Is the answer going to be yes, it is related, or no, it's not related to the wavelength, the period, and the frequency, or the frequency? What do you guys think?
Would it wouldn't be related to the, well, to the wavelength, because you don't need amplitude to find that out. I mean, you could.
Yeah, so is it related or it's not related?
I would say no. So then, what would be related? What would amplitude be related to then?
It's not related to any of these things. I hope that you guys are more in this class than Jose. So I'm hoping that everybody else wakes up too. Okay.
Okay.
Okay. So what do you think? Is it related or not related? Do you see A at all in these things? And he's asking a very good question. What is it related to then? It's going to come down the road. It's related to the power and the energy, the amplitude. Okay? But not to this, guys. These are related to just the type of medium that you have in question. Okay? The wavelength, frequency, and the wave speed. Those are related to the medium where you have the wave is waving, basically. Okay? But the amplitude depends on the source. Okay? You could have a very, very bright light or a very dim light, both of them producing electromagnetic waves. One of them is intense, high intensity, high amplitude. Others are low intensity, low amplitude. And both of them, they could be the same color. Both of them can be red lights. One of them is the battery is running out, or actually manufactured so that it doesn't produce a lot of intensity, versus another one that has a lot of intensity. Okay? So do you see that? So the power should be related to the intensity, and that's to the amplitude. Okay? Intensity is the power.
So a wave can have a short wavelength and a high amplitude, and also have a short wavelength and a low amplitude.
Yes, the amplitude has nothing to do with the. Hopefully, you guys are. I know. Okay. First of all, the wavelength can be anything, short or long, medium range, whatever you like it. Okay.
Right.
Now, depending on the medium, the frequency will be related to that. How short it is versus how high the frequency is. Okay, that is true. But the amplitude, how bright it is, or how, basically, for sound, for example, I can say my P, which is the letter P, which has a certain tone in it, which is certain frequency in it, and a certain wavelength, since I'm sitting in here and you're going to hear it, okay? But I can say it soft P, or can I scream at you with a P, okay? Do you understand? What I changed in here is the amplitude.
Okay.
The frequency did not change. The wavelength did not change. The speed of the wave did not change. What changed, if I scream at your ears, is just the amplitude. Okay.
So it's just stronger, like going in the y-axis. If you looked at it from a graph perspective.
Yes. Yes. So your sergeant, when you are doing your training, can get you high intensity there. Okay. You guys see the difference? But the same letter can be the same thing. I can tell you, okay, give me 5, or I can scream at you. It's the same thing. Okay? Same frequency, same wavelength, same everything coming at you. but with different intensities. One of them can actually rupture your ears if you go next to it for a long time, actually with loud speakers over 140 decibels over an extended period of time. It can actually do damage to your ear, okay?
Is voice like just one wavelength, like,
No,
or can it be different as
it
well?
is different. That's how the brain interprets it, actually, with some of them
Oh.
high pitch, some of them low pitch. For example, if you hear, I mean, typically, for example, a small child has a high pitch frequency, and an older man, for example, has a low pitch, and basically that's how the tones is. Not only that, actually, the words themselves, as they come to us, they come
Right.
with different frequencies, and that's how some words, they come basically flat, some of them they come peaked, and that's how the brain interprets them, basically. As a matter of fact, we have a range between 20 to 20,000 hertz that we can hear. Okay, that is our range for the human ear. For a bats, they can really hear much higher frequencies that we can, and that's why sometimes and actually dogs also. And that's why you can annoy a dog with a high frequency whistle, but you cannot hear it yourself, and he's really annoyed with it. And whales, on the other hand, and elephants, they communicate with low frequency that we can't hear, but actually they could be very loud talking to one another, but we cannot hear it because it passes the low frequency things. That's really some of the things that are fascinating with frequencies. But the intensity can be very soft, very low intensity, very low amplitude, or very high amplitude. Same thing with light. It can be super bright light, or it can be dim light. So that's where the amplitude come into play. Okay, but it doesn't, it's not related to any of those. Does this make sense to everybody? Okay, so let's continue. Now here is where it starts talking about the definition of transverse wave. Okay, transverse wave. You have a wave that is propagating in the x direction, correct? But the disturbance is happening in the y direction. Okay. You are supposed to go and click on that link. And in this animation, you will see several dots, and the dots, you will see them going up and down. Okay. Up and down as the wave is moving from left to right or right to left. Okay. So that is transverse wave. Longitudinal wave is when, like this link in here I was demonstrating earlier, that is actually a longitudinal wave. Sometimes it's called compressional wave. So you compress it, okay, and it's going to travel in that direction, okay? The same direction of travel is the same direction of compression, okay? So that is x direction is the direction of travel, and x direction is the direction of also the disturbance. So this is called a longitudinal wave. In the case of an earthquake, they're at the P mode and the S mode, the P wave and the S wave. So one of them is transverse and the other one is longitudinal, okay? That is basically what they refer to in seismic waves. So again, you're supposed to go and look into this, and you're gonna see something called compression, which is in this case a compression basically of the medium, followed by a rarefication. So the medium is actually oscillating back and forth. So if you take a dot, it's going to go back and forth, that's all, okay? It never travels to the other end. So the material doesn't travel, it just goes back and forth. But this whole disturbance is traveling from one side to the other side until it leaves the medium, okay? So that is basically longitudinal, sometimes called compressional waves, okay? So you'll have a dot that is colored red. This is done to make it easier to keep track. Does the red dot move across the screen with the wave? So you really have to look at that and answer these questions. That's what I was talking about in here earlier. What does this move? What does move with the wave? Okay, so it's not the medium that is going to move. It's actually the energy at the end that is going to be moving. It's the disturbance. Okay. Remember earlier I said something about the amplitude. Here is where the amplitude comes into play. And when you talk about power. Power is the rate at which the energy is flowing from one end to the other, okay? There are some factors in here, I didn't write them. So when you see this curly thing in here, that means it's proportional. Okay, not equal, proportional to the square of the amplitude and the velocity of the wave. Okay, fast moving wave has more power, it dumps more power, more energy per second than a slow moving wave. Okay, so that is expected. And the intensity or the amplitude squared is what matters, not the amplitude itself. In front of this expression, there are two terms that I didn't write. 1/2 of times the density of the medium times, that's basically the other terms that I'm not writing in here. Okay. So what matters in here is, the point in here of this discussion is the amplitude squared is related to the rate of which the energy is transferred. They're related to the energy actually. And also the velocity matters also. A fast moving wave will dump energy faster to the other side than a slow moving wave. Okay. If the wave is not moving at all, if V is 0, then there is no energy transfer, there is no wave. Okay. The water waves are a little bit different. So you really have to look at the animation in here, because what happened in here is it's like a circular motion. So the whole pattern is the waves move sometimes with the direction of motion, sometimes in opposite direction of motion, sometimes up, sometimes down. So it goes down in circles, okay, on the surface of the water. So again, you're going to follow the dot and you will see how this water waves on the surface behave, okay? There is a link for that. It's on YouTube, okay, actually, too. By the way, all of these links, they are actually on under my account, so you can clearly go there. But I made sure that these are not public, okay? So you really have to click on them there. So if you look for them, you're not going to find them. You have to really follow the links, okay? Torsional waves, if you have string, for example, and you twist it, okay? And you let go of it. So again, this twisting will travel through the medium. I don't know if you saw that in the bottom. So those are different kinds of waves too. So those are also waves that require torsion, motion on both sides. Again, there is an animation for that. Circular waves, they travel in a circular path and they move in directions. Again, there is a link for that. So you are required to do all of these links. Okay. You may have noticed the main difference between the above 5 waves types is, so basically 5 in this case is, let's start from the beginning. Transverse, longitudinal, water, torsional, and circular, okay? 2 are fundamental, and 3 are just a combination of the other 2. Okay, that's all. And the 2 that are fundamental are these 2 actually. Because in the case, for example, of the torsional, I mean, in the case of the water waves, you have a motion back and forth. It looks like it's longitudinal compressional, but in the same time up and down. So it's a combination of the 2. Every single motion can be broken down into these 2. Okay? So that's basically in a nutshell. But I really want you to pick up on those things and try to see the patterns and how it's doing it. Okay? So far, question 7 talks about a different kind of wave. That is not really a wave at all, okay? And that is quantum waves, okay? You heard probably something in quantum mechanics called quantum waves. And they have actually a wavelength where this number h bar is a constant, which is 10 to the negative 34 joules per second. They have an energy also associated with them, but they themselves, they're not actually waving anything, okay? So they're actually, every single particle in the universe has its own wave function, and it's called a wave because it's really a mathematical wave, no more, okay? So I just want to bring that attention to you guys, and you will see how this combined to make particles, okay? So again, this activities, there's 3 videos in here, including the GeoGebra link, and how to get the group velocity. This is the question that is, I'm going to leave it to you optional, because trying to understand a little bit of quantum waves is a little bit outside of the scope of this course. Since this lab was actually part of another lab or another class that I use, I left it there, actually, but you have the option to answer this question, okay. Which of these animations has the phase velocity moving faster than the group velocity? Again, I was talking about that waves, they come in packets, and in this animations, you will have two waves, okay, combining in a group velocity, in a group of them. One of them will be moving faster than the group. The other one probably is going to be behind in this case. So which one is faster depending on their color coded? You're going to answer that. Is it possible that the phase velocity can move in the opposite direction to the group velocity? The answer to that, yes. Okay, as long as you have more than a wave. So could the phase velocity move faster than the speed of light? Okay, that is something depending on the medium. Okay, so if you want to answer this question, I want you to really refer to those videos, the colors and things like that. If you want to skip it, that's fine. Okay. Reflection. So these are the types of waves. So there are two parts in this lab so far. We covered first of all the properties of the wave, namely the wavelength, the velocity, the wave velocity, the frequency, the amplitude, and the period. Okay, and the group velocity to some extent. Then we discussed the types of waves. Okay, and we discovered at least 5 of them, 6 of them if you include the other one. But those are the types that we discussed in here. And then we're going to talk now of wave phenomenon. What happened to waves? What do they do? Waves, when they interact, what do they do? When a wave hits a medium separating two media, it's going to be reflected. Okay, this is regardless of the wave. Okay, when, for example, you step in front of the mirror in the morning trying to fix your hair, actually the light is coming from the light source, which is sometimes a light bulb in this case, hitting your whatever, your hair, and then bouncing back on the mirror in front of you, giving you a replica of your hair. Okay, and the only reason why you get an exact replica in this case is because of the law of reflection. The law of reflection says the angle of incidence must be equal to the angle of reflection. Okay, it's very, very important to define what these angles are. Here they are. The angle of reflection is the angle, so this is the medium separate, this is the mirror if you wish, okay? The mirror separating you and the material that is basically behind it, whatever that is. So I hope you guys know by now that there is no other you on the other side. It's only a reflection, okay? So, and it follows these rules, okay? So the angle of incidence, all of the angles are measured with respect to the normal. The angle of incidence is not this one. Where is my pen? Can I get comments in here? What is the comments tool in here? To see if I can get mine. And use pencil, maybe? Can I get this thing in here? Yeah, it's not this one, okay? That is not the angle of incidence. So the angle of incidence is this one, okay? This is the normal to the surface. This is the surface, okay? Equals to the angle of reflection. R in here stands for reflection. So this law is known in some books as Snell's law, named after the guy who made it popular, Snell's law. There are 2 of them, okay? Number 1, or the Snell's law of reflection, okay? The angle of incidence equals to the angle of reflection. This doesn't matter what wave is it, whether optics, which is the electromagnetic waves, we're looking at the mirror, or sound waves, okay, echoes and things like that, or waves bouncing off of surface, for example, on water, once they hit a medium and they bounce back. So the same principle, okay? So if you send a water wave at an angle to a medium, it's going to bounce back on the other side, and the angle of incidence must be equal to the angle of reflection, okay? So this is how a wave behaves in a medium separating the two.
is this kind of like when you're looking at a mirror and then you kind of like look sideways and you see like, you know, you look at a, you're not looking at exactly you, like if you're seeing it from an angle, right? Like you're seeing the opposite angle, like you're seeing the
Yeah.
opposite.
Let me illustrate the image, how the image forms, because image formation is one of the most fascinating topics in actually optics. Okay, so let's talk about that because you brought up this issue. So let's see how the image forms. Okay, so let me share with you the screen. So here is the image. Here is the mirror. I'm sorry. Oops. Why it doesn't write on the screen now? Is it because they changed colors? No. Okay. So here is the mirror. Okay. Let's say this is you. I'm sorry. I'm a very bad in drawing in here. Okay. Let's give you some eyes in here. Okay. So you're looking at your feet. Okay. Here is the light reflected from your foot down to your eye. Okay. This angle of incidence is equal to the angle of reflection. For you, when you see, because this looks like it's the same angle, so this is the Snell's law, it looks to you as if the image is coming from the other side. This is, for you, it looks like this coming like this. This is where your foot is, okay? You look at your hand, for example. Again, we're going to draw Snell's law. So for you, this is where your hand is, okay? Look at the other hand, for example. It's going to give me a different. The angle of incidence is this angle. The angle of reflection is this one. So for me, it looks like it's coming from the other side. So, and there is another you. If you look at your eye, actually, it's going to go straight out. And it comes by, it bounces back. For you, it looks like it's coming from here. So there is another you on the other side that you can form, basically, just by following this pattern, okay? So that's how the image forms. The distance from here to here, the same distance from here to here, okay? The height is the same, okay? And the magnification is the same. So there is an exact replica of yourself sitting on the other side. The only thing that changes actually is the left becomes right and the right becomes left. That's all, okay? Look at this hand in here. It was on this side in front of the person. Now, for you, it looks like it's behind him. That's the only thing that flips, okay? The left and right. Everything else is the same, okay? So that's how the image forms for a flat mirror. For a convex mirror or concave mirror, it's completely different mathematics. In that case, there is actually a magnification. That is the ratio of the heights or the ratio of the distances, okay? And for this, and it depends also on the focal length. In other words, how curved it is, okay? Optics is fascinating in here in this case. And also, this is not the only object that form images. Also, lenses do that too. And you have two types of lenses. There are lenses that are concave and lenses that are convex. And lenses that are in between, they use both combination because the lens is curved from both sides or curved this way, both sides. So it's fascinating. I have a lens in here somewhere. Here. Okay, I have a lens in here. Okay, so that's actually a convex cam. Anyway, and using corrective lenses for optics for people like myself, for example, who have problem seeing, is a fascinating thing too, because you want to bring the image back so that it falls on the retina so that your eye can interpret it. Again, we drifted a little bit, but it's okay. So this is the topic of the reflection. And this is one of the laws that govern nature, and it's true for all waves. That's fine. Okay, so that's the image formation and how the image forms. So to go back to your question, if you stand this way, it's still the angle of incidence equals to the angle of reflection. So the image looks like it has shifted to the other side too. Okay.
And the angle would be greater at that point, right? It would be equal, but just greater?
Yeah, it's because you made it greater. So if theta I moves in such a way, can I still try it in here? If theta I, for example, becomes this one, you're going to have this way, okay? So this is still true. This is the angle of incidence. This is the angle of reflection. Right? So the object now looks like the object now is here. Oops, what happened in here? I clicked on the link. Sorry. Are you still looking at the PDF?
Yeah.
Yeah, the image looks like it's in here somewhere. Okay. And now I completely messed up things. Control 0. Bring it back to scale. Control plus. Okay. And let's delete that. I don't know what that is. So the image looks like it's forming in here somewhere. Okay. From you standing in here. Originally, for this one, if you follow it, it looks like it's on the other side here. So you move it in here, the image moves with you. Okay?
Mm-hmm.
Fascinating stuff, optics. This
Mm-hmm.
is, if you had a chance, any one of you is moving toward the physics classes later on, the calc-based physics for Physics 4 series? Because that's the subject of Physics 4C. Okay. Anyway, for which of the two reflected waves can the boundary point move? Okay. So you're going to look at the videos in here. Okay. Reflections come in two different waves, in phase and out of phase. So the reflected waves can be in phase, meaning that basically in sync with the original, with the incidence, or out of phase, basically flipped. Okay. So, for example, let me give you an example with the medium in here. So if I had to take a string and attach it from this end, okay, and I make a disturbance, so that disturbance will travel through the medium until at some point it's gonna be hit the wall, and once it comes from the wall, it's gonna come from the bottom. So this is an out of phase. It shifted by 180 degrees. Sometimes when the medium is free, there is like for example, I put it around with an opening like this. So when the string hits it, it's going to go up and down, and the wave will come from the top too. So it's still in phase. Okay. So again, you need to really look at the animations and try to decide on these things. Okay. Now there is one that is going to be out of phase and one that is going to be in phase. I already answered the question 8, the one where where the boundary can move, that is going to be in phase. The other one should reflect back. Okay. If you don't believe me, take a string, hopefully a rope, okay, and try it outside. Tie the rope to the pole and then create a disturbance, and you will see the disturbance traveling through the rope. When it comes back, it hits the rope because it's tied to the other side, to the tree, for example. It's going to bounce back on the bottom. It comes back to you from the bottom and yanks you from the bottom. Now, if you put it in a ring, for example, on a pole, so that you can keep track of it, that's all. Otherwise, you can let it free on the other side, okay? To move, then it's going to stay in phase, basically stay on the top. But then you have, if you're going to leave it free completely, without a rope, you have to really create several times. Otherwise, it's going to lag. It's not going to stay on the same medium. But if you go, pull a string, put it on a ring and a pole, and then let go, give it a snap and watch it. It's going to go up. And then once it hits medium, it's going to rise with the medium and come back with it and come in the same direction on how you sent it. Okay?
So that would be in phase, right?
That would be in phase. Okay? Now watch these videos and see if you can change your mind. This is a tricky thing. You really have to do this activity several times in order to answer it. Okay? Now this is the sound that you hear again. That is the echo in this link. That's what I was saying earlier. I mean, this lab is mostly watching and trying to understand what's going on, go through the definitions and try to answer them. Okay?
Is this what you know how basically like those monitors that track like heart rates? Is that what they're basically doing? Like what we're seeing, like you know how like in the hospital how they have those waves? Like is that?
I don't know how those devices work, honestly.
Because it looks like kind of like those waves that we're seeing right now. That's I wanted to just ask.
Yeah, I know that it's used in, for example, geology extensively, and I don't know if you're aware of the latest articles on Mars, for example, in astronomy. They're talking. They found a lot of oceans under, not oceans, I'm sorry, lakes under the surface of Mars. And basically, how they did it, they use this technology where they send waves. And based on the waves when they reflect from different media, for example, when it hits the surface of Mars, as it reflects back, that is one reflection. Then it goes down, absorbed by the surface of Mars and goes down. And when it sees a separation of medium, it's going to bounce back. Based on that, you can determine the thickness of the medium and its density, okay? Now, it reflects on the lower part of the surface, and they found basically in some places of Mars, at least within a few kilometers, that they have a lot of, at least 3 lakes they found them so far, of salty brine water in there. And that is why now they are more excited than before in expecting that maybe life actually still exists under the surface. The only trouble with that is they don't know where it gets its energy, because if it's that deep, it's about 1 kilometer deep under the surface of Venus, I mean, surface of Mars. If that's the case, then the water is there. Is there life in it? That's another thing. How did they find out? By using the reflection of the waves on the surface, different layers that it reflects. They determine its thickness, they determine its density, and determine all kinds of properties of that surface. So it's interesting. So maybe it's the same technique used in hospitals. I don't know, honestly. But at least for this one, it's a different things. It has a lot of other applications too. Okay. In the pipelines, when I was in another place, actually, I met this engineer who had a problem, and he was dealing with it, trying to basically what they do is they send waves, and based on the reflected waves, they determine the status of the pipeline, basically, that conducts natural gas from place to place. So depending on the characteristic of the wave that bounces back, they determine if the pipeline is still in good condition or it has started to become corroded or other
corroded.
problems. Yeah. So
is that because different wavelengths can go through different types of matter?
Yeah, they can go through different types of matter. Not only that, it gives you the specific properties of, first of all, the soil, and also the layers there in terms of their status. Do they have a lot of corrosion? Are they leaking? Do they have a problem? Is there probably a problem from the other side where it says that the pressure has dropped, for example? So they want to find where to fix it instead of digging the entire pipeline, which is very costly. So they want to send waves, and then once they find it, okay, that's the point where we should start digging and fix the pipeline. Okay. So,
that's interesting.
Yeah, so he was an engineer working for a company of natural gas, I guess. No, it's actually oil company. And I was actually teaching in the college there, at the university there. So he approached me about the problem, trying to do things like that. So this is used extensively a lot in all kinds of applications. Okay. Okay. So do you observe wave reflection for all situations? Tensile waves, light waves, water waves, sound waves? We just answered, obviously, yes. All waves do that, okay? For light and water waves, do you see the incident and reflected angles as about equal? When sound waves reflect, what do you call that? Okay, so again, you're going to go through all of these activities, okay, and do that. And what is called the sound when it reflects from the mountains? Does anybody know what the name for that is called?
Yodeling? Just kidding.
Anybody? Okay, Taryn thinks it's echo. Does everybody agree with Taryn?
Yep.
Okay. I think that's what it's called, okay? There is a funny story by Mark Twain on people collecting echoes. Okay. Anyway, refraction is another property of waves, okay? When a wave hits two different media, it's going to be refracted. Basically, in this case, the angle of incidence again and the angle of refraction in this case, okay? Not the angle of reflection. We don't have reflection anymore. I mean, sometimes we have both, refraction and reflection, okay? That's why if you stand on a pond, you could see yourself, the reflection basically on the surface of the water, but also you can see underneath the water, so you can do both. So you can have both. So it's not always impossible to have both of them. The
Refraction would be the fish that you could see underneath, and reflection would be you.
Yes. The light in this case is not going straight through. Okay. So the assumption here is the index of refraction N1, Ni, is less than the index of refraction Nr. Okay. Otherwise, if Nr is less than Ni, the refraction will be greater, will be this way. Okay. So the assumption in this picture is Ni is less than Nr. For air, Ni is equal to 1. Practically 1. It's not exactly 1. For vacuum, it's 1. Okay. So Nr, or N, the index of refraction, really is the ratio of the speed of light in the medium, in this case water, versus the speed of light in vacuum. I'm sorry, the speed of light in vacuum versus the speed of light in the medium. Light travels a lot slower in water because it's absorbed and transmitted, than it does in air, which is very little interaction of the molecules of the air. That's why the index of refraction is practically that of the vacuum. Okay. In a thicker medium, like for example glass, it even travels with a different velocity. Okay. So light is always refracted in different media, provided that the medium is not completely opaque. Okay. It's transparent. It has transparency in it. So again, the law that governs it is this law. The index of refraction times the sine of the angle of incidence, this is the angle of incidence, is equal to the index of refraction times the sine of the angle of refraction. This is the word I'm going for in here, okay? Not reflection. The first one was reflection. This one, okay? This is a refraction now, okay? So this R now is that of refraction. Watch the video, okay, that you do. You may notice that refraction is always in phase. That is good to know. Also pay attention to the wavelength of the frequency, the frequency, and the wave speed, okay? If you watch it, you see that they don't really change, okay? I'm sorry, they do change slightly, okay? One of them changes, but you really have to watch it very closely, okay? Because of this relationship now, because of the velocity itself changing. Is the wavelength of the refracted wave different from the incident wave? How about the frequency? Okay. One of them will be different. Not both though. The speed will change also, okay? That is important. So you really have to watch these videos and tell me which one is which. The wavelength is a separation between wavefronts, okay, as it's refracted. And so it's going to change. The frequency should not change because that's how they came in. Since now one of them has changed, remember that the wavelength over the period, or wavelength times frequency, is the speed. Since the wavelength now is changing, the speed has to change accordingly, okay? So that's really the thing with it. Here is the thing on how to do it with light. Take, for example, a blue laser or a red laser. I used to have a red laser, I don't know what it is. And send it through glass, for example. You see the color does not change. So the frequency doesn't change. But it's refracted, so it has to go through slower through the other medium. So that means the velocity has changed, meaning that the appearance for it, at least the wavelength, should shift accordingly. Okay? And that is why we have another thing called dispersion, which we will see later on, that how rainbows form actually when light is refracted with different angles. Again, you're going to watch these videos and try to answer the questions. Okay, this question, you don't have to answer it in here. Okay. And then do your observations for refraction simulate for both light and water. Can you cite other examples of wave refractions? Okay. So we're trying to think in here, okay? See if you can find others. Now, which brings me to question 12. Question 12 involves another slide, another PDF file that you need to open. And that is the second worksheet that you guys have, which is the refraction worksheet. And it tells you that you have 4 angles, alpha, beta, gamma, and delta are illustrated in there. With which angles corresponds to theta I. So which one of the angles that are given in there is actually theta I, the angle of incidence? Which angle corresponds to the angle of refraction from alpha, beta, and gamma? And use the table. In the table, they give you actually the sign of this different angles. And given that n is equal to 1, ni is equal to 1, I'm sorry, this is ni. So this number is 1. Okay? You're supposed to find the ratio of the, since you know what the angles are, find their signs, and from there determine the index of refraction of the material, okay? Calculate the index of refraction. So let's open that file, okay? Let me stop sharing this one in here and go to it. I think I had it open already. Here it is. So alpha is 47 degrees, beta is 43 degrees, gamma is 24 degrees, and delta is 66 degrees. Which one is the angle of incidence in here? Which one do you think is the angle of incidence?
47 degrees.
Is it 47 or is it 43? This is the medium. Let me comment this thing in here. See, this entire medium has an index of refraction n1. This entire medium has an index of refraction that we don't know what it is. It's an nr. This is the separation between them. This is the surface of the water, if you wish. This is the normal. And here, which one is the angle of incidence? I need you guys to tell me, based on definitions that we defined earlier.
Can you go back to the graph? I'm sorry.
Okay.
Okay, so if beta
Is it, which one? Is it alpha, beta, gamma, and that? Everybody now needs to vote on this, okay? This is
so
not...
if the angle of incidence is the one that's on the refracted side?
No, the angle of incidence is on the incidence side. It's on the air side.
On the air side. Okay.
Yes. Yeah.
So I would say, actually, you know what? I think it's going to be beta because isn't it if... Oh, it doesn't add up to 9 degrees there, right? Because I thought if it was like... Never mind. I'm not really sure.
Anybody other than Jeffrey, please? So you have 4 choices, either alpha, beta, or gamma, or delta. Come on, guys. This is not democracy. We really need to have a say in here.
I was gonna say, like if the beta was like the opposite of the 24 degrees, but I thought it added up to me, but I don't know. I'm not really sure where I was going with that, so
Okay.
I'm not. I don't know. I have
So
no idea.
Which one you are inclined to say? Out of the 4.
I was gonna say beta as well.
Okay. And who was that? Because I didn't see who was.
Oh, sorry, Amanda. Because I'm looking at the law of refraction, and then it says.
Okay.
That
anybody else support Amanda on this? Jeffrey is inclined there, but he's hesitant a little bit. I want somebody else to.
What was the answer? What was the question?
The question is, what is the angle of incidence? Alpha, beta, gamma, or delta?
Would it be Would it be gamma?
Okay, Jose thinks it's
Mm,
gamma. Amanda thinks it's beta. Anybody else? The angle of incidence.
hey, what's the 24 degree?
That's the
Oh,
gamma.
that's a gamma? Yeah, I think it's gamma.
Okay, let me delete all of these things. Okay. So the medium separation. So we have two media. Okay, we have this medium. This entire medium is 1. And this entire medium is 2. This is air. This is something else, water, for example. Okay. We need to find its NR to find exactly what it is. We need to find its index of refraction to know exactly what it is. At this point, we don't know. Okay, but it must be thicker than air. Now the question is, this is usually the incidence. This is usually where I'm coming from. So it cannot technically be gamma or delta. So it's either alpha or beta. This is the refraction side. So this is where my angle of refraction will reside. So the angle of refraction, really, I have two choices, delta or gamma. The angle of incidence are either alpha or beta. So I narrowed it down now. So Jose, it cannot really be gamma, can it? It has to either be alpha or beta.
It's gonna be beta then.
Okay, so I have Amanda and Jose, both of them thinking it's beta. Anybody else? Jeffrey, were you now more convinced, one or the other?
I don't want to say beta just because like they said it, but
No,
I'm just
no.
I'm just trying to figure that out. You know, like
Okay.
I don't know.
I have a question.
Yes.
So on the left side, right? It's coming in.
No. There is no left or right. There is up and down. So yeah.
The light's
Hey.
coming from the top, basically.
Yes.
The top, right?
Yes.
Yeah.
And then, is this kind of like the same example as you were giving us, where we're looking at our feet, so it looks like
No, that is a
on the other side?
reflection. That is a reflection.
Okay.
This is a refraction. This is a different story altogether. Okay.
Yeah, I don't know. I said beta because it looks like it would be kind of like reflection, but I mean, if it's refract, I don't know. I'll just stick with beta.
I know we have more than 3 people in here, and I need the input of everybody now. Okay, where is everybody else? Come on, guys.
So on alpha, it has a single line next to 47 degrees. I'm gonna take that as that's what the your eyesight. That's what you're looking at. And if it reflects down to delta or whatever with the 66 degrees, I want to say that's like your reflection.
So you're saying it's alpha?
I'm saying it's alpha.
Okay, so we have 2 betas and 1 alpha. I need everybody
Beta.
else now.
Just kidding.
Anybody else now? I need everybody else, please, okay? The rest of you guys. So we're going to put it in here. And I need everybody else. Samantha, Omar, Taryn, Alicia, Victor, Ontian. Okay. Samantha now thinks it's alpha. Okay, so we still have other people. So now we have 2 alphas and 2 betas. Come on, V. Okay, Victor thinks it's beta, so we have 3 betas and 2 alphas. Come on, guys. Alicia now thinks it's beta. Beta is gaining more grounds now. V is beta. Taryn is beta. Yontian is beta. Oh man, the guys with alpha are really only 2 lonely people now. Okay, still I did not hear from who? I think I have Omar. Okay, so let's go back into the definition. Let me go back into it. The angle of incidence is the angle between the actual wave, the actual signal, and the normal to the surface. That is how we defined it earlier. So this is the normal to the surface, okay? So this angle is between them, so it must be beta. You guys see that? So theta I is 43 degrees.
Oh, so that right side is water, basically, right?
There is no right. It's all of it, the bottom one. Okay.
The bottom one.
Yeah, the separation is this one. This is the separation. This is
Right.
the normal to the separation, the perpendicular to the separation. Okay. So let me draw it probably in different color too. I don't know if I have different colors on this thing or not. So let's see if I can change color on this one. Properties, can I get a different color? Yeah. So this is the separation between them. It's in blue. The normal is in red. Okay. So that is actually the separation between the two media. I have two media in this case. I have air and something else. Okay. So the angle of incidence is 43 degrees. Now, this is not over yet, everybody. Okay. I need to find the angle of refraction, theta r. And theta r, you really have two choices. Is it 24 degrees or 66 degrees?
24.
I want to say 24 as well.
Okay, so we have two 24s. I need everybody else. So they're saying gamma. I need everybody else now for the angle of refraction. Is it gamma 24? Or is it the other one? I forgot even how much the other one. 66. 24 or 66?
No, I think it's 24 too.
Okay, so we have three 24s. Okay, Victor's 24. Come on, V, Taryn, Omar, Wantian. Did I hear from Alicia already? I don't think so. Alicia thinks it's 66. I need everybody else to wake up. So if you guys are V, Taryn. We're talking about the refraction. We're not talking about the incidence, okay? The incidence, we settled it and it's done. Okay, now we want the refraction. So the choices are gamma or delta. So let me go back into the picture. Gamma or delta. So the first one was the incidence and we resolved it to be beta, okay? The second one, that's because it's by definition the incoming wave and the angle it makes with the normal, okay? So it must be beta, 43 degrees. Now the question has nothing to do with the incidence. Now we're talking about the refracted wave. So this is the refracted wave, okay? And we want to know the angle of refraction, is it 24 or is it 66, okay? So come on, V and everybody else. Okay, Wantian thinks it's 60, V thinks 66, 66. Who I did not hear from? Taryn, did I hear from you? Amanda, did I hear? I think. Okay.
Amanda Lopez, I said 24.
No, not the Amanda or Elena. The other Amanda, sorry. I need at least one more person. Okay, Taryn now supports the 24 idea. So there was a split now, 50-50. Again, let me go back into the definition. Go always with the normal to the surface separation, okay? Don't look anywhere else, okay? Look at the normal. The normal in this case goes from top to bottom in the two media. So in this case, the refracted wave is this one, and the normal is this one, and this is the angle they make together. So the correct answer is 24. Okay. So now we have answered the first part of the question, which was the angle of incidence is beta, and the angle of refraction is gamma. Okay. Now we need to apply that law. Okay. We need the sine of 43. I need to find first where 43 is in the table. Here is where 43 is in the table. I need to find the sine of 24, because that's the angle of refraction, 24. Here is 24. Here is its sine, 0.4067, and the other one is 0.6820. And take the ratio of the angle of incidence over the angle of refraction, namely 0.682 divided by 0.4067 times 1. That is my NR. So let me go back into the other one. So this, we thought it's 43. This, we thought it's 24. Okay? This is given 1 for air. From here, we should be able to find the NR. Just do the ratio of the two. Does this question make sense now? So we know what medium it is now. Okay? Since we know its index of refraction, we can go to the tables and look at what medium has this index of refraction. All indices of refraction must be greater than 1, because nothing moves faster than light. Okay? The index of refraction always more than 1. So if you find an index of refraction less than 1, you should really be alarmed, because that is not possible. Okay? Does this question make sense now? Do you guys understand how to do this one? Yes or no? Okay.
We're just trying to find the change, right? Like
we find the ratio. We find how thick the medium is. This index of refraction that we find tells me how opaque, or how basically how much it really transmits light. Okay, that's basically what we're trying to do. The opacity of that medium. Okay, how fast light travels in it. Because the index of refraction also, there is another definition for it, which is the speed of light, c, divided by the speed of light in that medium. Since this number is always bigger than this one, so this number is always bigger than 1. So it's going to travel slower in that medium. So this number in the denominator is less than the speed of light in vacuum. So this is 300,000 kilometers per second, or 300 million meters per second. This one is going to be less. Okay? So this index of refraction is always going to be more than 1. So we actually determine the type of medium. Now, in addition to reflection and refraction, waves do diffraction. So basically, here is a wave. These are wave fronts coming, okay? When they hit the medium separation in here, they can bounce back. That is fine. We can understand that. But when there is a small opening in the separation, depending on the size of it versus the wavelength, waves can be transmitted from it. And this point becomes a source now of waves. And these waves travel, and there are new wave fronts in here. And depending on the size, now you will have it more or less diffracted, okay? So this is a diffraction. This is not a reflection. This is not a refraction. This is a diffraction, which is a different kind of behavior, okay? Diffraction is very, very important because that's what allows you to hear somebody who is on the other room. You could be in this room and somebody has the TV loud in the other side and you can hear it. So a reflection, if the frequencies were, I mean, you can't see the TV through the door because light is reflected, so it's not transmitted through the wall, okay, or the doors since they are closed. But the diffraction will allow the sound to go through because, and again, how much the wavelength is related to the curvature, so they go around it. But light doesn't go around it, so you can't see the TV unless you're actually facing it up, okay? So again, this is another behavior. You're going to watch this one in here and see how light is diffracted from different openings, and you make it smaller or bigger. Interesting videos in there and how to see them. Now, do the wavelengths, frequency, and speed change? No, they don't. The amplitude will change depending on basically how much intensity passes through. Okay. Then there is another behavior for waves, and that is the interference. Okay. Two waves colliding with one another. So if they come peak to peak, they will have a higher peak. But if they come peak to trough, then they will cancel one another and you will have nothing. In general, depending on how much they are, they will have different structures, okay? You're gonna go through the links and complete them. And in the peaks, you have constructive interference, and the troughs also is constructive from the other side. And where they cancel, you have nodes, okay? When they are in phase, they are constructive. When they are out of phase, they are destructive. Okay. You have two sources of waves, okay? And in the points where the maxima meets, you will have bright spots. In the points where the maxima can come out of phase, they cancel, you'll have dark spots, okay? So in a sense, you could be living near the ocean, and you could have your boat on this side and not feel the waves at all if they are transmitted on two different openings and you happen to be where the waves cancel when they come out of phase, okay? Or the waves will be twice as intense if you happen to leave where the constructive waves happen, okay? So again, you're going to have the lights basically with constructive and destructive interference. And you're going to discuss that for water and light, and they should be similar, okay? Now, there is another behavior for light, and that is for waves in general, and that is beats. When you have the frequencies are different, but not too much difference, they're very close from one another, you will hear a hum, okay? And the beat frequency is defined as a difference between the two frequencies. If they come with the same frequency, then you can have constructive or destructive interference. There is no problem with it. But if they come with different frequencies, then you can have beats. Okay. So that is the answer to that. Again, piano tuner, basically what he does is, he has a tuning fork, and I used to have one next to me. He sends the note, and he knows exactly what that note is on the piano, for example. So he sends the same note. If the piano is in tune, he should not see that hum. He should not see the beat frequency. If he sees the hum, he has to adjust frequency, the tension actually in the tensioner, enough so that the frequency of the beat will match that of the tuning fork. So in this case, he has to go higher tension or lower tension depending on that to bring the frequency up or down of the piano to make it match so that now the piano is fully tuned. Okay, again, that is how you use the beats in this case to adjust that. Dispersion is another behavior that I talked about. Light, when it comes in, the white light that is going to be dispersed. And it's dispersed really when it's refracted, okay? The different wavelengths, they are refracted. The short wavelength, they are refracted the most. The long wavelength, they are refracted the least, okay? And that is how actually rainbows form, okay? By having light coming from the sun broken down into its components, and we'll see the different basically colors in the spectrum. They're broken down basically of light in the case of what is that phenomenon? The rainbow, okay? What is this ROYGBIV mean? Does anybody know? Can anybody guess what?
Red, orange, yellow, green, blue, indigo, violet.
That is it. So I want you guys to be, that's part of another discussion, okay? I know it's part of the question, and that's question 17, but that's basically how they are, okay? Because red is a longer wavelength than any of the others, and violet is the shortest wavelength. Violet is the most basically dispersed versus red, which is the least, and that's how the spectrum forms. You guys understand the second question in here of the day? So ROYGBIV is exactly, I don't know who mentioned, was it Amanda?
Yes.
Amanda Lopez, okay, please, thank you very much. Okay, so that's how Amanda mentioned it, so that's part of the discussion for today, okay? So that is how light is dispersed, in this case using a prism. Okay? So that's the question 17 actually too. So again, in this case, there is the echo, okay? And do you hear the sound quality? So in this case, you're gonna hear, and the quality of the sound will change. So you need to really pay attention to the echo and how it forms, okay? Brings us to the Doppler effect. The Doppler effect is a connection between a source wave, okay, and observer. I have actually two observers in here, observer 1 and observer 2. The source is moving toward observer 1 and receding from observer 2. Wavelength in here appears the distance between them is longer. So there is an apparent behavior for the frequency in this case so that they look like they're lower frequency, okay? And for when it's approaching an observer, the waves are compressed and they look like the wavelengths are shorter, so which means it's a higher frequency. Because for you, sound doesn't change, the velocity with which it moves. Your perception of the pitch changes. Without looking at the source, you could tell if the source is coming to you or not just by studying the frequency of the sound, okay? This is true for sound, true for light, true for everything, okay? So this is when the source is moving. When the observer is moving and the source is stationary, it's the same thing. The source is stationary in emitting sound waves or emitting waves in general at constant rate. Now the observer is moving towards it, rushing to meet them. So he will see them with a higher frequency. Whereas this one, the waves are coming toward the observer and the observer is moving away from them. So they appear to come a space between them. So again, they appear to be longer wavelength, meaning the longer wavelength, meaning lower frequencies, okay? The time between them is actually longer, meaning that they are less and less of them per second, okay? So this is two scenarios really, either the observer moving toward the source or the source moving toward the observer, and it's similar results, or the source is moving away from the observer or the observer is moving away from the source. In general, it's both, okay? In general, the observer could be moving toward the source and the source moving away from him or moving toward him, and combination, I mean, it can be complicated very quickly. So again, you're gonna watch the Doppler effect and answer the questions, okay? You're gonna hear the sound again of the incoming and outgoing whistling. And you're gonna document your observations, okay? Is it possible for our light to do that? Absolutely, okay? And that's how we discovered actually that the universe is expanding, because we discovered that frequencies from specific emissions are shifted toward the red, hence the universe is expanding. Which brings us to the concept of resonance. The concept of resonance is really when you have things in sync. For example, in the case of the swing, you can bring it to resonance. Every time it comes back in here, you give it another push. So in this case, it's gaining more and more energy per cycle. Whereas, for example, if you give it a haphazard push, it's not going to be in sync. Okay. So when things are in resonance, okay. And this is the case, for example, when the standing waves, in the case of the string, will from the source of the vibrations, when they hit the wall, if you time them correctly, you will have actually standing waves forming on it, okay? So again, you need to watch the videos and answer the questions. The question of polarization is another behavior in here. For example, for the electromagnetic waves, it has specific direction for the electric field. you can have light eliminated from all directions only from a specific direction, and that's what the polarizers are for the glasses, used for driving in the sun to help you see better. Instead of seeing a fuzzy picture in front of you, you will see a much clearer picture using polarizers. Does this happen for sound? Absolutely not, because sound really doesn't have it moves in compressional waves, so if you cannot to do that for sound, you have to do it only for transverse waves, not compressional waves. Here is a question. Transverse waves can be polarized as the up or down side. What are the orientation of circular polarized waves? So at the end, you're going to have one direction. Why can water waves not be polarized? Again, because similar to sound, okay? Okay, and then you're going to come up with a conclusion of all of these explorations of the different things. So there are three things that we explored today. Three things. First of all, the properties of waves, namely wavelength and frequency and all of that thing. The types of waves, that is also we thoroughly explored that, okay? And there are two basic types and some derivative types. And then we explored also interaction of waves with media and with themselves. With media through reflection and refraction and diffraction and all kinds of other behavior, with themselves through interference and basically beats and other things that we have explored. So three things: properties, types, and interactions of waves. So we explored everything that has to do with waves today. Okay, any question? If you guys don't have questions, right now it's 7:46 p.m. The lab ends at 9:10 p.m. So what I'm going to do in here, I'm going to leave it to you guys if you want to stay in the lab. I'm going to stop the recording after basically these instructions. So I'm going to leave the session open until 9:10 p.m. Waiting for the last person to leave. Then we're going to end the session, or we end it at 9:10 p.m. If you have any questions, just shout the questions. I'm going to change the speakers so that they can move around. Go and get something to drink. And that's it. Any questions for me before we stop the recording? So that other people don't know. Okay, the angle of incidence, somebody asked it, so let me go back to it. It's similar to the angle of, whether for refraction or reflection, both of them are the same thing. So it's the angle, let me change this, why am I moving too slow? There are 18 pages in this instruction, okay, there are a lot of them. So again, in the case of a reflection, the angle of incidence, so you have here a medium, and you have here the normal to the medium. The angle of incidence is the angle with the incident wave and the normal. Okay, so this is your angle of incidence. The angle of reflection, in this case, is the angle made by the reflected ray and the normal to the surface. Now for the case of refracted waves, it's the same thing. What matters is the normal. I have medium in here. This is air, could be air. This entire region is air, and this entire region is water, for example. This is the separation between them. This is the physical separation between the two. This is the surface of the water, if you wish. This is the normal to it. As the ray is coming from this side, the angle it makes with the normal is the angle of incidence. As the ray is refracted, again, the angle of refraction in this case is the angle made with the normal, okay, which is this angle. So that is basically basic optics in this case. If you have difficulty with this one, please ask it again, because I probably will have a different activity similar to this one's, using probably other means in here. So the change in the direction of a wave due to a change, this is the commonly observed when a light wave passes from one transparent medium to another at an angle between 0 and 90 degrees. It is common to express the speed of light as a matter of index of refraction. So that's what N stands for. It really stands for the speed of light in comparison with that in the vacuum. So if C is the speed of light in vacuum and V is the speed of light in matter, then N is equal to C over V. There is a problem in here. Okay, I'm sorry, I need to fix this one in here. So this is N equals to C. Please correct this one in here. That is going to be part of the discussion in here. It's C over V. And I wrote it already before. I wrote it somewhere in there during the instructions that this is actually what N stands for. Okay. So please make this correction. That is actually added now to the discussion so that everybody need to know that. Okay. There is a question on the refraction, which is on page 8. The definition of N is actually C over V. Okay, so that's really an expression for what that is. So the law of refraction, the product of the index of refraction and the sine of the incident angle relative to the perpendicular, what I've been calling normal is the perpendicular, okay? For the incident medium is equal to the same product of the refracted medium relative to the to perpendicular again. Does this make sense to the person who asked a question? Question came. Okay, very good. Okay, guys, so I'm going to stop the recording now and leave the session open until you guys leave or the time expires.